Okay, everyone. Assalamu alaikum and hello. Let's begin with our today's class. We were doing differentiation, and today we want to cover the last concept that we have in this, and that's rate of change. Okay, that's the plan for today. Let me just check if everything is working fine. Yeah. Okay, so in the last session, we learned about increasing and decreasing functions. What are increasing functions? Increasing functions are functions that have a positive gradient, and decreasing functions are functions that have a negative gradient. And since for uh, functions we find gradients using the derivative, so we can say whenever we have an increasing function, the derivative is supposed to be greater than 0. When we have a decreasing function, the derivative is supposed to be less than 0. Now, there are some functions that are increasing in some part and decreasing in another part. For example, this one and this one. And then there are some that are throughout increasing or throughout decreasing, right? So the first, the ones on the left side, they are increasing throughout. And the ones on the right side here, they are decreasing throughout. Okay. So we talked about these functions. Then there were a few examples that we did. This was question number 14 that we did in the last part. We had to find the set of values of x for which it was an increasing function. What we did for that was we found the derivative, and we put that derivative greater than 0. That gave us a quadratic inequality. We solved that quadratic inequality to find the set of values of x for which the function was increasing, right? And then we did a couple of other examples in which we had to show that a function was increasing or decreasing, right? So there was one question number 36 in which we had to show that the function was increasing. Now in this case, we did not start with this inequality. We had to show that this was always positive. So we found the derivative first, and we used the derivative to prove that this derivative was basically always positive. That's why since the derivative has a minimum value of 1, we said that it's always going to be greater than 0. That's why it's an increasing function. Similarly, we did another one in which we showed that it was a decreasing function in which the derivative was always negative. Okay. Now, let's look at the last concept that we have in this topic, and that's the rate of change. You can also let me know in the chat box, by the way, if you have any questions from the worksheet until this point, and we would most likely discuss them towards the end of this class. If not this class, maybe next class. I would ideally want to start our next topic in the next session. But let's see. If you still have questions after today, we will see if we can spend maybe one more class on differentiation. So rate of change and chain rule, this is what we want to do today, first of all. Okay, so I can see some questions that you have asked. Let's quickly have a look at them and see how important those questions are in our discussion. Question number 9. Okay. Question number 19. Okay, so basically these are questions involving diagrams that you are kind of confused. And I think the part that you're probably finding difficult is the first part where you have to prove something. So that's basically related to mensuration. That's the second part is pretty straightforward after that, which is in which you just have to find turning point. But okay, we can have a look at the first part of this. And question number 9 as well. I think you would have the same problem in the first part, in this case, proving this. So it's more of a mensuration problem rather than a differentiation problem. But okay, we'll discuss them. We'll do them. Let's first discuss this last concept that we have, and that's the rate of change and chain rule. Okay, so first of all, we need to understand this terminology of rate of change of something. So this dy over dx that we calculate, derivative of y with respect to x. Remember what this represents? It represents the gradient of a function. Dy over dx, that's basically rate of change of y with respect to x. So in the numerator you have change in x, right? Dy is basically change in x, and you have dx, that's change in y. Change in y over change in x, that's the gradient. There's another way of describing this, we can say this is the rate of change of y with respect to x, right? So dy over dx can also be understood like this. Dy over dx, rate of change of y with respect to x. What that means is, if we were to increase x by 1 unit, how much would y change because of that? Right? That's what it means. If we were to change x, if we were to increase x by 1 unit, how much would y change because of that? So we say this is rate of change of y with respect to x. Now, we won't always have y and x. We could have some other variables as well. For instance, if you have something like this, if you have dy over dt, what does that mean? Now, using the same logic, we can say this means the rate of change of y with respect to t. Okay, if we have dx over dt, we would understand that as the rate of change of x with respect to t. Right? So whatever you have in the numerator, you say rate of change of that variable with respect to what you have in the denominator with respect to the variable that you have in the denominator. Right? Rate of change of y with respect to x in the first case, and then y with respect to t here, and then x with respect to t here. Now t here represents time. And in a lot of cases, when we refer to rate of change, we assume there to be time in the denominator here. So a lot of times when we refer to rate of change, we would be referring to rate of change with respect to time, right? So mostly when it just says rate of change of something and it doesn't specify which variable you're talking about, you assume it to be time. So they won't always mention time here. If it just says rate of change of x, that means rate of change of x with respect to time. If it says rate of change of y, that means rate of change of y with respect to time. So if they don't specify any variable with respect to which you are finding the rate of change, the assumption is that that variable is time. So mostly when we talk about rate of change, we're going to be talking about rate of change of something with respect to time. That, okay, in 1 second, how much does this variable change? All right, so rate of change would mostly be with respect to time. Okay, so if you just have rate of change of y given, you would say that's dy over dt. If it's rate of change of x, you would say that's dx over dt. And similarly for any other variable. Okay. Now, let's try to understand how we're going to actually use this rate of change. Let's try to understand that using an example. Let's say we have a container that looks like this. So I'm going to make a cylinder like shape here. Let's say we have this. I'm just going to copy this. Okay, so let's say you have a cylinder that looks like this. And let's say we're given that the radius of the cylinder, the radius, that is 5 meters. So it's a big cylinder. It's kind of a tank. So it's a big tank basically. And the radius of this tank is given to be 5 meters. So let's call this R. And we're given that R equals 5 meters. Okay, that's the radius of this tank. Now what we're doing is we're basically pouring water into this tank, let's say. So we're pouring some water into the tank like this, and the water is being poured such that the rate at which you're pouring water, that's 2 meter cube per second. So water is being poured into this container at a rate of 2 meter cube per second. Okay, that's what you're doing. Now, what happens when you pour water into this container? The water level is going to rise. So let's say there's some water in the container like this. As you pour more water, it's going to keep rising, right? Now, let's define three variables for this example. Let's say we have one variable that's V, and that represents the volume of water in the container. Okay, so let's say we are representing volume of water in the container by V. And then as the water level rises, the depth of the water is also going to increase. So how do you measure volume? You measure volume in, you measure water in terms of if it's volume. It's a 3D thing, right? So in order to measure water, you say, what's the volume of the water? That's one thing that's increasing. Volume of water is increasing. At the same time, as the water level, as the amount of water in the container rises, what also rises at the same time is the height of water or the depth of water in the container. Let's call that H. So with H, we are representing height or depth of water in the container. Okay, that's another variable that we've got. And then let's say we have another variable that's time, and that's represented by this letter T. We have this variable. So we are pouring water in this container at a rate of 2 meter cube per second, given that the radius of this container is 5 meters. Okay. Now, let's say you are basically asked something like this. Given that the rate of or let's say given that you are pouring water into the container at a rate of 2 meter cube per second, find the rate at which the height of water in the container is increasing. Okay. Well, yeah, let's actually call it a tank. It's a big cylinder. So we say it's a tank. This is what we've got to do. Given that you are pouring water into the tank at a rate of 2 meter cube per second, find the rate at which the height of the water in the tank is increasing. So we know the rate at which the volume of water is increasing. Now, how do you write that down? Volume of water, rate of increase of water, rate of change of volume, rate of change of volume. How do you write that? We'll say that's dV over dt. Volume of water is represented by this letter V. The water is being poured into the container at 2 meter cube per second. That means every second, the water level, the volume of water is increasing by 2 meters, 2 meter cube. So we say that's rate of increase of volume or rate of change of volume, dV over dt. We say that's 2 meter cube per second. That's the information that we're given. What do we want to find out? We want to find the rate at which the height of water in the tank is increasing. The rate of change of height. That is what we want to find out. Abdullah, just give me a couple of minutes. dV over dt is given. dH over dt is what we need to find out. All right. This is the information that's given. This is what we want to find out. Now, how do you find this out? Let's try to understand this. So we know this is what rate of change means now. dV over dt, that's the rate of change of volume. dH over dt, that's the rate of change of height. What we want to find is dH over dt. Okay. Now for this, we would need to have some kind of relation between the volume of water in the container and the height of water in the container. So we want some equation that connects the volume of water and the height of water. Okay, so we want some connection between them. Now, what's the volume of a cylinder? Water just takes the shape of whatever the container is, right? So this cylinder has a volume of pi r square h. The water volume is also going to be given by pi r square h. So given that the height of water in the container is h, what is going to be the volume of water in the container? We can say that's going to be pi r square h. Right? So we have a relationship between v and h like this. We know the radius of the container, that's 5. We can put that here. We can say that's pi into 5 squared into h. And that gives us v equal to 25 pi h. That is how volume and height are connected to each other, related to each other. Now, this is the information that we have. We know that dv over dt is 2. We know that dh over dt, we have to find dh over dt, and we know some relationship between volume and height. Now we will do this using a rule that we call chain rule. So what we're looking for is dh over dt. What we say is we want to find dh over dt. Right? This is what we want to find out. Now this can be found using two fractions like this, using a product of two fractions like this. dh over dt, right? This is what we need to find out. We do this using chain rule, and the chain rule works like this. We write two fractions, and they have to be multiplied together. The numerator of the first fraction here is going to be the same as the numerator here, dh. That's, we put the numerator of this fraction as the numerator of the first fraction, and the denominator of the second fraction, this place, this is going to be the same as the denominator of this original fraction. So we break that down into two parts like this. dh over dt, we break down into two fractions like this. We break it such that dh is the numerator of the first fraction and dt is the denominator of the second fraction. And then in the remaining places that we have here, we have whatever is the third variable. So dh comes as the numerator of the first fraction, dt comes as the denominator of the second fraction. Now, what's the third variable that we have here? We have h already here, we have t already here. The third variable, the variable that's left, is the volume. So in the third place, we say we have dv here and dv here. So we can write dh over dt as a product of these two fractions. We can split it like this, dh over dv into dv over dt. Now, you could kind of think of it like this, that this dv and this dv, they are the same, right? So you could kind of cancel them out, although that's not a very mathematically correct way of thinking about this. But in order to remember this, you could do it like this. You could say dv and dv, they will get canceled. What are we left with? dh over dt, and that's exactly what we want here. So how are you going to write down this equation? You're going to split the fraction into two parts like this. You'll write two fractions. The numerator of the first fraction is going to be the same as the numerator here, and the denominator of the second fraction is going to be the same as this denominator. And in the third place that's left, you write the third variable. Using this equation now, you can find out dh over dt, the rate of change of height. How do you do that? dv over dt, you already know the value of that. They have given that in the question. The rate of change of volume with respect to time is 2. So in this place here, we put 2. Okay, in place of dv over dt, we put 2. The problem is dh over dv. Where do we get that from? This is where this equation is going to be helpful now. V equals 25 pi h. Using this equation, what we can do is we can say, let's find dv over dh, right? If we differentiate it, what's going to be the derivative of this? dv over dh, v is the subject, So in place of y, we've got v here. In place of x, we've got h. So we say dv over dh. What's the derivative of 25 pi h? Remember, the constant outside remains as it is. So 25 pi, this whole thing is a constant. Pi is also a constant, remember. 25 pi remains as it is. And then you multiply by the power. The power of h is just 1. So multiplying by 1 would not make any difference. And you subtract 1 from the power. What does that become? H raised to power 0, which is just 1. So the derivative of v with respect to h is just 25 pi. Just like if you had y equals 25 pi x, what would be the derivative of that? Dy over dx? That would be 25 pi. We've just changed the name of the variables. Instead of y and x, we've got v and h here. That gives us dv over dh equal to 25 pi. And now what we can do is, now that we know the value of dv over dh, we can put that here. We have dh over dv here. We can say dh over dv it's the same thing as 1 over dv over dh, right? If we take reciprocal of this, that's going to be this thing, dv over dh. So if dv over dh is 1 over 25, if dv over dh is 25 pi, dh over dv is going to be 1 over 25 pi. We just take reciprocal of that, right? If we take reciprocal of this, we get dh over dv as 1 over 25 pi. And that's what we input here. That gives us 2 over 25 pi. You can just evaluate this on a calculator now. 2 divided by 25 pi. And that's giving me 0.0255. That's the rate of change of height with respect to time. So if the volume of water is increasing at a rate of 2 meter cube per second, the corresponding increase in height every second would be 0.0255. This is the rate of change of height with respect to time. Okay, so that's the concept of rate of change. Rate of change of y means dy over dt. Rate of change of x means dx over dt. Rate of change of v, the volume means dv over dt. Rate of change of height means dh over dt, right? That's the notation that we use here. And then using this rule called chain rule, you can find the unknowns that you have. So sometimes you could have dh over dt given, and you might have to find dv over dt or some other variable. You might have to find the rate of change of area in some cases or any other variable. You can make a chain rule like this. How is the chain rule going to work in general? If you have 3 variables, let's say x, y, and t, and let's say you have to find dy over dt. How would the chain look like in that case? You make 2 fractions, you write 2 fractions. The numerator of the first fraction is going to be dy. The denominator of the second fraction is going to be dt. So we have dy as the numerator of the first fraction, dt as the denominator of the second fraction. And then in the remaining place that we have here, you've got the third variable. What's the third variable here? X. So the chain will look like this: dy over dx into dx over dt. That will give you dy over dt. Similarly, if you had to find dx over dt, if that's what you were looking for, how would the chain look like? The numerator of the first fraction will be dx. The denominator of the second fraction will be dt. And then in the remaining places here and here, you're going to have the third variable, whatever that third variable is. In this case, the remaining variable is y. We put y here and y here. So dx over dt can be found as dx over dy into dy over dt. All right. So you'll have some information given. You'll have to use that to find some missing information. This is how you use a rate of change and chain rule. That's the idea. That's the concept. Now you should be able to do all the questions from the worksheet. Okay, so that's all in terms of concepts that we need to know. Now we will be looking at some more questions from the worksheet, but I'll start with some on chain rule, and then in the next class as well, we will spend at least the first half of the class on differentiation, And then maybe we can start integration after that if we have enough time after that. So now let me know if you have any problems in this. Abdullah, I'm sorry, you had a question. Can you
Sir,
ask that now?
sir,
Yes.
from the statement, how did you get dv over dt equals to 2?
Okay. You are pouring water into the tank at a rate of 2 meter cube per second. Water is being poured into the tank at 2 meter cube per second. The water level is rising by, the water is increasing by 2 meter cube per second. How do you measure water? Water is measured as volume, right? Volume of water. So the volume of water, that is increasing by 2 meter cube per second. Now, if you don't understand that very clearly from the question statement, you can also understand that from the units here. 2 meter cube per second. Meter cube is the unit for volume. So we're talking about volume over time. So it's the rate of change of volume over time. That's dV over dt.
Sir, so why can't it be the other way around as time is also increasing as the volume of water is increasing? Why can't it be dt over dv?
It's meter cube per second, no? Volume per time. It's not second per meter cube, it's meter cube per second. And dt over dv, that also does not make sense logically, as in you don't say that for every volume, every 1 unit of volume increase, time is increasing by this much. Time is an independent thing. Time does not depend on anything else. Volume is depending on time here. So volume is what you have in the numerator and time is what you have in the denominator here. But it's clear from the unit as well, as in it's meter cube per second. That's dv over dt.
Sir,
All
so
right.
time will always be in denominator.
No, not so in the chain rule, it could be in the numerator. But when you write rate of change like this, when you write rate of change of something, then yes, time will always be in the denominator. If you have to put something the other way around in the chain rule, you will take reciprocal of that. But when you talk about rate of change of something, then yes, time is always in the denominator. So if you're talking about rate of change of x, that's dx over dt. Rate of change of y, that's dy over dt. Rate of change of volume, that's dv over dt. All right. Because they're
Okay, sir.
talking like this, that for every 1 unit change in time, how much is that variable increasing or decreasing? Any problem with this? Any questions, anyone? Any other questions? No. Okay, now sometimes you might have something decreasing as well. So if they had, for instance, here that the water was leaking out of the container at some rate, what's the rate of change of height with respect to that? For example, you could also have something like this, that you have a container and water is leaking out of that at a rate of 0.1 meter cube per second. If that was the only thing happening and there was no water being poured into the container, how would you write dv over dt in this case? How is the volume changing? What's the rate of change of volume here?
Negative.
Anyone?
Negative.
It'll be negative, right? It'll be negative now. So you'll say this is minus 0.1. So if it's an increase, you use a positive number here for the rate of change. And if it's a decrease, you use a negative number for the rate of change. Okay? Make sense?
Sir, can you explain it again? This part. How is it negative?
If you have a container and water is leaking out of that container at some rate, let's say it's leaking out at 0.1 meter cube per second, is the volume of water increasing or decreasing when the water is leaking out? Is the volume
Decreasing.
of water going to, it's decreasing, right? So every second what is going to happen to the volume? It's going to decrease. So every second, the volume is going to change by negative 0.1. dV over dt represents change in volume. Now, since that change is negative, since the volume is decreasing, the change is negative, it's going to be negative 0.1. Okay.
Sir, so in this case, we have already found dV over dt.
We have already found dV over
dV
dt.
over dt. Yes.
That's given. That's given. So they've given that
Okay, sir.
water is
Okay.
leaking out of the container at 0.1.
Okay.
Okay. All right. So if it's a decrease, you use a negative rate of change. All right. If volume is decreasing at 0.1 meter cube per second, you would say dV over dt is negative 0.1. All right. Okay, so that's it in terms of concepts. That's all that you need to know about differentiation. Now, let's do some questions, some more questions that you have. So we'll do some today and then in the next class as well. Let's start with a question on rate of change, first of all. What we've just discussed, chain rule and rate of change. So let's start with a simple one. Imad, the question that you have sent, is that related to rate of change or is it something else?
Yes, sir.
Okay, so let's start with a simple one on rate of change, and then we'll do one that Imad just sent. Let me start with one from this worksheet in which they're talking about rate of change of something. Okay, so I think we could start with okay, let's start with this one. Question number 11 from the worksheet. Now it's a relatively simple one. Let's quickly do this. Then we do another one after this. Question number 11 from the worksheet. Okay, so it says the equation of a curve is this. In the first part, you have to find an expression for dy over dx. Now, let's do the first part. Y equals 12 over x squared plus 3. How do you find the derivative of this function? You first have to write this in power form with x in the numerator. Right now, it's in the denominator. You have to bring that to the numerator. So it becomes y equals 12 into x squared plus 3 whole raised to power minus 1. Okay, so first of all, you write it like this. 12 into x squared plus 3 whole raised to power negative 1. Now you apply the power rule on this. dy over dx, what is that going to be? 12 remains as it is. You multiply it by the power. The power is negative 1. You subtract 1 from the power, so that gives you x squared plus 3 whole raised to power negative 2. And then you multiply with the derivative of the part inside the brackets, the base of the power. The derivative of x squared plus 3 is 2 times x. Now, let's simplify this. That gives you minus 12 into 2x. That's going to be minus 24x whole divided by x squared plus 3 whole squared. If we write this negative power in the denominator, the power, the sign of the power is going to change. It's negative 2 right now. It becomes 2. That's dy over dx. That's the first part. Now, in the second part, they ask you for the equation of the normal to the curve at this point. Now, that's something that you can do. Do we need that for the last part? No. So second part you can do, just have to find the equation of the normal, right? How do you do that? You have the derivative, put value of x here, 1. That will give you the gradient at that point. Take negative reciprocal of that. That will be the gradient of the normal. Then you just use this point along with that gradient and put that in the form y minus y1 equals m into x minus x1, right? The second part is pretty straightforward. You can do that. let's have a look at the last part that involves the rate of change. A point is moving along the curve in such a way that the x coordinate is increasing at a constant rate of 0.012 units per second. So what does it mean? What does it mean? X coordinate is increasing at a rate of 0.012 units per second. How do you write that in mathematical form? In the derivative form, you can say dx over dt, right? That's what they've given. Rate of change of x coordinate is 0.012. Find the rate of change of the y coordinate. So what we want to find is dy over dt. This is what we need to find out as the point passes through P. So when do you need to find dy over dt? We need to find dy over dt at the point P. That means when x equals 1 and when y equals 3. So these are the values of x and y given that we might need to use. Now let's try to think about this. Dx over dt is given. Dy over dt is what we have to find out. How do you make a chain for this? Dy over dt is what you're looking for. So say dy over dt. That should equal a product of two fractions. The first fraction is going to have dy as the numerator. The second fraction is going to have dt as the denominator. And then the third variable comes in the middle. What's the third variable here? The third variable is x. So we have dx here and dx here. Okay, now we just need to input values here. Dx over dt. What's dx over dt? Dx over dt is 0.012. The problem is dy over dx. What's dy over dx? Dy over dx is this thing. Let me write that here on the side. Dy over dx is equal to minus 24x divided by x squared plus 3 whole squared. Now, in the previous example that we did, in this simple example, the derivative that we were getting here, that was just a constant, right? We did not have to input any value of x or h there. We were just getting a constant. We just put that directly in the chain rule here as 1 over 25 pi, right? However, sometimes what happens is the derivative that you have, that is in terms of a variable. So it's in terms of x. That is why they've given you a value of x that you should use here. They're saying what's dy over dt at the point P. Now, what do you know about P? At the point P, the x coordinate is 1, right? The x coordinate is 1. So in order to find dy over dx at this point, you put x equal to 1. And that is going to give you dy over dx at the point P. Let's see what that turns out to be. Minus 24 into 1 divided by 1 squared plus 3 whole squared. And that's going to give you minus 24 divided by 16. And that's minus 3 over 2. You put this value there. And that chain rule, dy over dx is minus 3 over 2. And I just evaluate this and see what that turns out to be. And see what that turns out to be. Minus 1.5 into 0.012. And that's giving me minus 0.018, that is dy over dt. This is the rate of change of y at that particular point. Make sense? Any questions on this?
No, sir.
No? No problems? Okay, now let's have a look at another question. Let me just copy that here. Okay, let's try another question on rate of change. So this is from a recent paper, apparently, 2021. Let's have a look at this. Okay, so it says volume of a large circular mound of iron ore of radius r meters is modeled by the equation V equals this for r greater than equal to iron was added to the mound at a constant rate of 1.5 meter cube per second. Find the rate at which the radius is increasing at the rate when the radius is 5.5. Okay, let's think about this. Part A. What information are we given? We are given that the volume is modeled by this equation. So this is what volume is. V equals 3 over 2 into r minus 1 over 2 whole cube minus 1. And we're also given that r is greater than equal to 2. So this is only defined for r greater than equal to 2. Now, iron ore is added at a constant rate of 1.5 meter cube per second. What's this? 1.5 meter cube per second. What is this information? How do you use it?
dv over dt.
It's dv over dt. It's the rate of change of volume with respect to time, right? Meter cube, that's volume. So we can say we have one piece of information given here, that's dv over dt, that is 1.5. Okay. Now, what we need to find is the rate at which the radius is increasing at the instant when radius is 5.5. So what we want to find is we want to find the value of dr over dt when r equals 5.5. Okay, dr over dt, that is what we're looking for. Now, please don't input this value of r here directly. You can't input the value of r here directly. That is just going to give you the value of volume at that particular radius. You're not looking for volume. You can only input this value of r after differentiating. So you are looking for the rate of change of volume, the rate of change of radius, the rate of change of both of those things, not the actual value of the volume. So you're not going to input r first. You're first going to differentiate it, then put the value of r. Okay. Now, first of all, let's make a chain. What do we need to find out? We want to find dr over dt. What's dr over dt going to be? Let me write that here. Dr over dt. The chain is going to look like this. Dr here, dt here. In the middle, you have the third variable, which is v in this case. So we have dv in the middle. Now, dv over dt is already given. That's 1.5. What about dr over dv? You have dv, you have v in terms of r here. What you can do is just differentiate it. Right? Just differentiate it, and that's going to give you dv over dr. Okay, and then we can just take reciprocal of that at the end to input here. Now, what's dv over dr? How do you differentiate this function? 3 over 2 is a constant that remains as it is. Multiply by the power is 3. Whatever is inside remains as it is, r minus 1 over 2. Subtract 1 from the power, that's going to become 2. Multiply by the derivative of the part that's inside. What's the derivative of r? 1, right? R is like x in this case. So the derivative of that is 1. Derivative of this constant is 0. So we just have to multiply by 1. That does not change anything. Derivative of minus 1 is just 0. Now we can simplify this. We get 9 over 2 into r minus 1 over 2 whole squared. Now you can input that value of r here after differentiating. You can only do that after you've differentiated. Now put that value of r here. What does that give us? Put r equal to 5.5. That gives us 9 over 2 into 5.5 minus 0.5 whole squared. That's 5 squared. That's 25. 25 into 9 over 2. What do we get from this? dv over dr? Anyone?
45 over 2.
45 over 2. That's dv over dr. Now we put that here. dr over dv. If dv over dr is 45 over 2, what about dr over dv? That's going to be 2 over 45. multiplied by dv over dt, that was 1.5. And that's going to give you the result. This is going to become 3 over 45. 3 over 45 is 1 over 15. So that's the rate of change of radius with respect to time. Okay, so Hazem is telling me something else. Let me actually try this. 4.5 into 25. That's okay. I'm sorry, this is not 45 over 2. This is 225 over 2. Dala?
Yes,
That's
sir, I didn't took
225
the
over 2.
square.
Okay, 225 over 2. Now we just uh, let's take reciprocal of that. That's 2 over 25, 225. Let's see what that gives us. 3 over 225. That's 1 out of 75. That is dr over dt. You can leave it like this if you want to write that as a decimal. That will be 0.0133, minimum 3 significant figures. And that's how it would look like. Any problem with this? Is this all right?
Yes, sir.
Okay, let's have a look at the second part now. Part B. Now it says find the volume at the instant when the radius is increasing at 0.1 meter per second. Okay, now the first part is not relevant anymore. Okay. Now it's some information given about the rate of change of radius, and they're saying radius is increasing at 0.1 meter per second. How do you write this down in derivative form? What would you say?
dr over dv.
dr over dv. Why v? Dr
No,
over
sir, d
dt.
dt. Yes, sir. So,
Yeah, so dr over dt, right? So dr over dt is 0.1. That's what we're given. dr over dt, that is 0.1. Okay. At this instant, we want to find the volume. What's the volume formula? The volume formula is 3 over 2 into r minus 1 over 2 whole raised to power 3 minus 1. We want to find the volume at the instant when dr over dt is 0.1. Now for that, we need to find the value of r at that point, right? Because volume is defined in terms of radius, right? So if we can find the value of r that corresponds to this thing, we can just put that value of r inside this function, and that will give us the volume that we're looking for. Now, how do you find the value of r when dr over dt is 0.1? Let's think about that. So the rate of change of radius is 0.1. Now, we already have dv over dr found. We found that here. dv over dr was this. This is dv over dr. This is one thing that we have found already. And the question also told us that the rate of change of volume with respect to time is 1.5. That's constant. So that's still the same, right? So dv over dt, that is still 1.5. Now, given this, can we find the corresponding value for dv over dr first of all? So then it's on side. We have dr over dt, we have dv over dt. What we can do is we can find the corresponding value for dv over dr, because that will then help us find the corresponding value of radius. I'm sorry, I copied the wrong thing here. This is the expression for dv over dr in terms of r. Okay, this is dv over dr. What we can do is, using these two pieces of information, we can find out what dv over dr is. And once we find that out, corresponding to that, we can find the value of r. That value of R then can then be input here in the function to find the value of volume that you're looking for. So remember the question. The question says, find the volume. Volume is what you need to find out at the instant when radius is increasing at 0.1 meter per second. Volume is supposed to be found using this equation. We need some value of R for that. How do you find that value of R? You're looking for the value of R that corresponds to dr over dt being equal to 0.1. Now let's use chain rule to find dv over dr first of all. How do you make this chain? dv over dr is dv over something into something over dr. What's the third variable? It's t. So we have dv over dt into dt over dr. Let's just input those things here. dv over dt is 1.5. dt over dr will be this. That's 1 over 0.1. And that's going to give you 15. dv over dr is 15. Okay, so we get that dv over dr is equal to 15. Now just replace dv over dr by 15 with 15. You get 15 equals 9 over 2 into r minus 1 over 2 whole square. That is going to give you the value of r that you were looking for. When dr over dt is 0.1, the corresponding value of r will come from this equation now. How do you solve this equation? You can take 2 to the other side and then divide by 9. That's going to give you 30 over 9, which can be simplified to 10 over 3. 10 over 3, that equals r minus 1 over 2 whole squared. Okay, now you take square root on both sides. When you take square root on both sides, that's going to give you r minus 1 over 2 equals plus minus 10 over 3 square root. You get two values of r from that. R minus 1 over 2 is either equal to square root of 10 over 3, or r minus 1 over 2 is equal to minus square root of 10 over 3. Now, the second equation is going to give you a negative value. This is not possible because r is representing the radius, I think. Yeah, so r represents the radius. Radius cannot be negative. So this is not possible. What about the first one? What does the first one give you? What value of r do we get from this? Okay, so I'm getting 2.3257 from this. This is the value of r that we're now going to input in this equation, and that will give us the corresponding volume that we were looking for. And v turns out to be 3 over 2 into r, which is 2.3257 minus 1. Sorry, minus 1 over 2. Whole cube minus 1. Just evaluate this, and that should give you the volume at that point. 1.5 into 2.3257 minus 0.5 whole 3 minus 1. Yeah, so 8.13. That's what you get from this. Volume should equal 8.13 at this point. Okay, that's a lot of decimal values. So how many marks is this question? Part 2?
Sir, 3 marks.
3 marks. That's a lot of working for that, actually. Is this answer correct? Is the answer 8.13 for that?
Yes, sir.
Okay, let's just actually check if there is a quicker way of doing this in the marking scheme, maybe. So which question paper was this? Let me just have a look at that. P1. November 21. Okay, so it does turn out to be 8.13 at the end. So the answer is correct. But let's see if they have used any quicker way of doing this here. dV over dr, that's 15. Okay, so they found dV over dr first. And then they put that in that equation to find the value of R and put that in the volume equation. Yeah. Okay, so that's how we'll do it. So yeah, it does require some working, but yeah, that's what you do. Any problem with this?
No, sir.
No? Okay, now in the next class, let me know if you have any other remaining questions from this worksheet. Now you can do the complete worksheet. Also try one question from integration worksheet as in fact, which we haven't done yet, but there's a part that involves differentiation. I would want you to try that before the next class as well. Let me see if I can find that here. One integration. So this was. Okay, so along with the questions that are assigned from the worksheet, also try this one question. This is question number 48 from the next worksheet that we'll be working on. It's from the integration worksheet. Now, the first part requires integration, so you're going to skip that part. So to erase that from here. The second part is what I want you to try before the next class as well. Okay, so we have this curve, and it says the gradient of the curve has a minimum value when x equals 2. Show that, in fact, you have to show that the gradient of the curve has a minimum value when x equals 2, and also state this minimum value. Try this. We will discuss this in the next class as well, along with any other problems that you have. Okay. All right, that's it for today. I'll see you again on Tuesday night. Yeah, in fact, it's a long class on Tuesday. It's a 1 hour 30 minutes class at least. So that means we will be doing some more practice questions on differentiation in the first 30 to 45 minutes of the class. And then in the rest of the class, we will be discussing some concepts of integration as well. So we will start integration on Tuesday, inshallah. Okay. All right. Allah Hafiz, everyone.